All right, this is the last video. I think it's going to be pretty short. We're just going to cover two main topics in this last chapter on diffraction. Basically, what I want to look at is we want to look at the single slit diffraction pattern, try to understand why it happens, and then also understand diffraction grading. So basically, if you haven't noticed, the topic of this chapter is diffraction, and diffraction is a behavior of waves. And so what we're doing here is we're acknowledging that in this situation, light is acting like a wave because it's diffracting. What is diffraction? Diffraction is the bending of a wave around the edges of an obstacle or an opening. So basically the idea is that if a wave comes upon some sort of obstacle or comes upon an opening, it can pass through that opening or around the obstacle, but once it does that, it spreads out. And it's that spreading that is diffraction. A really simple example of this is the idea that if you are, say, in your room with the door open, you can hear someone talking outside of your room, even if they aren't standing right in front of the door. What is happening is the sound waves are diffracting through your opening of your door and coming into your room. Diffraction. I really like this picture because, not gonna lie, want to go swimming, want to go to the beach, but I think it's kind of a cool picture that shows these barriers in front of the beach are actually acting like barriers providing an opening, and then you can see the waves kind of coming, once they pass through that barrier, you can kind of see how they're spreading out, and that is diffraction. Now, one of the things that we want to study in this chapter is the diffraction of light, which can be a little unexpected. And here's a picture of demonstrating the diffraction of light, because basically what they've done is they've taken a ball bearing and illuminated it with a laser, and instead of creating just a sharp little black spot with the red light of the laser surrounding it, you see this really interesting pattern, which is caused by diffraction and interference. So let's talk about that. So if we use the idea of geometric optics, which is basically when we think of light as a ray, if we took a source of light and then produced a very straight barrier with a very sharp edge to it, we would imagine that what we would see on the screen would be the light and the dark where the barrier was, and a very straight edge in between them, a nice sharp boundary. Well, it doesn't really happen all the time. So in this picture, you have the light illuminating a razor blade, an old-fashioned razor blade. You might not be familiar with these, but you can see that the boundary around the shape of the razor blade is not sharp, and it actually shows these interference patterns that we see around the edges. What is happening is that the light, when it passes through the opening or the edges of the razor blade, are spreading out and interfering, so they're showing the diffraction behavior as well as interference. Now, something that's kind of important to understand about diffraction is when is it going to occur? And it basically has to do with the relationship between the size of the wavelength and the size of the opening. And I think that this visual is a really nice demonstration of how those two things interplay to produce either a strong diffraction effect or a weak diffraction effect. So in the first picture, what we have here is the wavelength is considerably, it's actually shorter than the opening. The opening is pretty wide compared to the wavelength. Keep in mind that the distance between these wave fronts gives you the wavelength. And so the waves are coming in on that opening, And when you look at the wave progressing once it goes through the opening, it spreads out a little bit, but really not too much. Now, if we switch things up and we let the wavelength be larger than the opening, we see a very strong diffraction once the waves pass through the opening. This is also an example of the wavelength being a little bit bigger than the opening, and we get a decent diffraction. So, what I would ask you, if you can answer the question, why do sound waves diffract more easily than light waves? Think about if you know something, for instance, I gave you the example a few slides ago that the diffraction of sound allows you to be able to hear someone outside of a room with an open doorway, but you couldn't, even if they weren't standing in front of the doorway, but you can't see them around the corner. It's an example of how sound waves diffract much more easily than light waves. So we're going to start off with just a single slit and look at the diffraction and the pattern that causes that. So again, if we treated light like a ray, we would assume that if we had some sort of barrier with a slit with some width, like call the width A, and we let the light shine on it, and we put that pattern on the screen, we would expect the pattern on the screen to be a bright spot that looks exactly like the slit. However, that's not what we see. If the slit is small enough, because that's important to see diffraction, we're actually going to see a set of bright and dark fringes on the screen. That's going to be the consequence of both diffraction and interference. Furthermore, there is a pattern to this, this diffraction pattern. It's brightest and most intense in the center, so that's like the central bright band. And then as we work our way outward, the intensities get smaller. And this is another thing that I talked about with the Young's double slit experiment, how you don't have just bright bands of color, but they sort of fall off as you get away from the center of a bright spot. It's sort of decreasing in its intensity in a relatively smooth way. And that has to do with the idea that the waves are, as you move away from the place where they perfectly constructively interfere, you start to get more of, they're kind of somewhere in between constructive and destructive until you get to where the dark band would be, and it's perfectly destructive interference. So this pattern is kind of similar to that for the double slit, but it's formed by a single slit. So, as we found with the double slit, when we think about how we would find, say, a bright spot, it does have to do with how the different light rays are interfering with each other. Again, now we're sort of using these rays, but remember it helped us with the double slit. So in this first picture, we have the light is just coming into the slit, if you have the line along where the slit is, the incoming rays are perpendicular to that. There's no angle to it, and so it's not that interesting. But as we look at angles, thinking about as the light would spread away, instead of talking about light coming from two different locations, as we did with the double slit, we literally think about how each of these rays might interfere with, say, a partner. And the easiest way to do that is to sort of divide the whole into two equal pieces, each one, and I'm going to show a picture on the next slide that's going to be more helpful. So if they kind of use some different labeling, it's kind of confusing. The things that you see here that mean that the the size of the slit is D, where over at top they call it A, which is kind of confusing, but anyway. So if this is D over 2, now if we look at the difference between the path length for the top ray and the bottom ray, they're different by a wavelength. And so at first we might go, oh, constructive interference. But what we do is if we split it into two pieces, we compare this light ray with this one, which is actually a half a wavelength out of sync. And so that these two are going to destructively interfere, and this one and this one are also a half a wavelength out of phase with each other. And so again, it's destructive interference. In general, we know that the difference in the path length between the top and the bottom is a full wavelength, but because we're pairing basically light rays with sort of their partners that are half a distance away, we actually find that for each piece at each location in the slit, we can find a partner source along the slit that would destructively interfere with, they destructively interfere with each other. And we have a whole bunch of pairs that are going to do that, where if we have a difference across the whole length that is more like a half a wavelength or some odd multiple of a half a wavelength, we're actually going to be able to find partners along the way that are only a wavelength out of sync with each other. And so those are actually going to create bright spots. Basically, we're finding that the rule for how to make a bright spot and a dark spot are exactly opposite of what we found with the double slit. This picture, I think, is a little bit more helpful, where they've taken the slit and they literally are showing the two light rays that are one from the very top and one from halfway through. And if those two are half a wavelength out of sync with each other, then of course you're going to get a dark fringe. And what that does is that's going to create the condition for destructive interference. And so if we switch out again, the labeling is confusing. The size of the slit, substitute for A, the D, and call the size of the slit D. If D sine theta, which corresponds to the difference in the path length, is between the top ray from the very top of the slit to the bottom of the slit, if that's equal to some multiple of the wavelength, it actually gives us destructive interference. And so this is the condition for dark spots on our screen. We can also then, if we say that, again, I'm just going to change that. If we say D sine theta is equal to m lambda for a dark slit, but we change this to the tangent of theta, because for theta small, the sine of theta and the tangent of theta are basically the same. And the tangent of theta is y over x, where x is the distance from to the screen. And so we can find the expression for the vertical position of the bright spots, the dark spots, is going to be m lambda x over d. And that's how we got this expression here. Again, I just want you to be sort of aware of the intensity variation for the single slit experiment. We're not going to cover the mathematics involved in that, but as I said, in general, you could think about how, as the light rays are interfering with each other, where they perfectly constructively interfere is going to be right in the center, but and where they destructively interfere is right here. But between these two locations, it's sort of a smooth variation from perfectly constructive to perfectly destructive. And that's why you get sort of that intensity variation as you go sort of along the edge of where the pattern is. Again, here's other pictures showing, and here, that what they've done here is graph it as a function of the sine of theta and where you're going to find those locations. So we can sort of extend some of these ideas. We've done the double slit experiment in the previous chapter, but what if we have multiple slits? Like many, like even maybe hundreds or thousands per centimeter on a piece of film. What this is this is called a diffraction grating, and this is actually something that is used. Diffraction gratings are actually really come in handy. What they are used to do is you can actually use them to take white light and separate it into its component colors, and it's basically like it's the interference and the diffraction, but because the different colors will interfere constructively at different locations, because remember, what's also in play is not only the angle, but the wavelength. And so different wavelengths will be at different angles constructively interfering. And so if you send the white light through this diffraction grating, you're going to see patterns. And here's another thing is, again, we're going to switch back, and then because the distance between slits is called D, and if you take two adjacent slits, if that distance in path is equal to a multiple of the wavelength, you're going to get constructive interference. I really wanted to see a picture, but so that's the condition for constructive interference. But let's look at what we see when we look through a diffraction grating. Because you have all these slits, but because you have d sine theta is equal to m lambda for where the bright spots are, the angle is going to depend on the wavelength. And so what happens is the blue light will constructively interfere at one location, green light interferes at another location, red light, etc. And so what it does is it separates the white light into all the colors of the rainbow. And so you'll see, if you look through a diffraction grating, and we would have if we would be in person, you could actually, you always can see the first order, like the first pattern of the rainbow. And also notice that you have mirror images. So like if you want to see it when you're looking through the scope that you would use, you actually would see one on either side. They're offset from each other. But then you might see something really faint even further over to the side, which is called the second order rainbow, because that is where the difference would be 2 lambda instead of just 1 lambda in the difference in the path length. So diffraction grating is really cool because it breaks the light down into its full spectrum, and this is actually a way then we can study the light, and there's actually much information that you can get from the light source if you study its spectra. Here's another picture kind of illustrating how the angle for, say, the violet light and its position is much different than that for the red light because of their difference in their wavelength. And so that helps you to understand why you would see the different colors arrive or appear at different orientations. Something that's similar to a diffraction grating is called a reflection grating, where you have the same sort of effect where the lights interfere constructively at a certain location, but instead of going through slits, they're actually bouncing off of grooves. And if you have an old CD, you might have noticed that they sort of can sometimes show a rainbow pattern because of the grooves that are cut into the disc to give the information, actually acts as a reflection grating. And finally, here are just some examples of reflection gratings from nature, one in an opal and the other one in the wings of a butterfly. And that is it for this semester. Thanks for hanging in there. We're all glad to cross the finish line, and let's have a great summer and hope that we'll be back in the fall.